Hello everyone, welcome to my YouTube channel. Today I will teach about the metal phosphine ligand. So phosphine is a spectator ligand. Spectator ligand means the ligands which are present on the metal center but don't take part in the reaction, although their electronic or steric properties can alter the reactivity of the metal complex. So phosphine are widely used as a spectator ligand in the organometallics chemistry. So phosphine ligand have the general formula is the PR3, where R group may be alkyl, aryl, halide, or hydride. So depending on the number of hydrogen atom replaced by the organic groups in pH3, the phosphine are classified total in three categories. One is primary phosphine. The general formula is primary phosphine is PH2R, where one hydrogen is replaced by the on R group. This is the primary phosphine. Another one is the secondary. The general formula of general general formula of the secondary phosphine is the PHR2, where two hydrogen is replaced by the organic R groups, and another one is the tertiary phosphine, where the general formula of this tertiary phosphine is PR3, where three hydrogen is replaced by the organic groups. So, and like the amines, phosphine have the pyramidal structure. So like this one, and it can function as a both nucleophiles and a base. So among these primary, tertiary, and secondary phosphine, tertiary phosphine are one of the most important ligands used in the organometallics chemistry, as their electronics and steric property can easily modify to fine-tune the catalytic activity of the metal center they are bound to. So, and closely related to this phosphide ligand, which have the general formula is POR3, that is widely used in the organometallics catalysis. So both phosphine and phosphide are two electron donors that bind to the transition metal through the lone pair. So phosphine is a L-type ligand. We donate total 2 electron to the metal center, and this is a neutral ligand. So there are the many example of, and this PR3, it is a monodentate phosphate ligand, and there are also many example of the polydentate bidentate phosphate ligand. So this is the some example. So this is the normal phosphine, and this is a trimethyl phosphine, is a triphenyl phosphine, trifluorophosphine, trimethyl phosphide, POME3. So this is the all are the monodentate phosphate ligand, and these diphenyl phosphonomethane, this DPPM, it is a bidentate, and this DPPE, diphenyl phosphonomethane, this also ethane, this is all are the bidentate phosphate ligands, and this is the chiral type phosphate ligands. So this is the example of monodentate and bidentate phosphine ligands. So phosphine are excellent soft donor ligands with variety of substituent which differ in steric and electronic properties. So variation of the R group. So variation of the R group can affect the electronic and steric property of the phosphine ligands. So this is the three main changes. So significant changes in the steric side of the phosphine, and changes in the basicity and necrophilicity of the phosphine, which in turn result in a large change in the donor acceptor properties. That means if the R group in the PR3, we can change if change by electron donating or electron withdrawing substitute, it can change the basicity or necrophilicity of the PR3. So that means that will affect the donor extractor abilities of this PR3 group, and preparation of variety of multi-dentate phosphines that can assume different coordination geometry and stereochemistry. So before going to the phosphine ligand, we should know the structure and bonding of the phosphine ligand. So this is the MO diagram of the phosphine ligand. So where the lone pair from phosphorylation is donate to the metal center, the empty d orbital of the metal, and here they also can extract the electron from its pi star orbital of PR3 from the field d orbital. So empty sigma star orbital of the PR bond phosphine R group plays a role of extractor of the metal complex of the PR3 as atom attached to the phosphorus become more electronegativity negative. The empty px sigma star orbital becomes more stable, so it moves the lower energy and become better extractor from the metals. So that means the R group in the PR3, which when the R group is more electronegative, that will stabilize more the sigma star orbital of the PR bond, so that will extract more electron to the metal center. That means the back donation is more when the R group is more electronegative. So this is the, so here PF3 is the more sigma extract the electron from the metal center. This is the increasing order the electron extracting property of the various phosphate ligand. When PF3 is the in when fluorine atom, this will more extract more compared to PCl3 or PME3 or PR3. So after that, another property of the phosphate ligand is the cone angle. So cone angle means the size or steric bulk of the phosphate ligand was determined from the simple 3D phase filling model of the phosphate ligand. So that means cone angle means total steric bulk of the P3PR3 group. That means how much space is occupied, that will determine by the cone angle. So this is the some cone angle of general phosphate ligands. So the importance of cone angle is that when there is R group is more steric bulk, that phosphine ligands has more cone angle, so that will occupy more space. So depending upon the cone angle, the ligand coordination number and the ligand dissociations, this is depend on the cone angle of the phosphine ligands. Another important is the bite angle. So bite angles mean the angle between the metal and phosphine ligands. So this is the bite angle. Here one bidentate phosphine ligand is bound to the metal center. So this is the bite angle is the PMP angle. So chelate ligand such as this ligand usually enforce the cis arrangement of the two phosphorus atoms as well as discarding the ligand dissociation by the chelate effect. So different chelates differ in their preferred bite angle, but many such ligands are very flexible, have a wide range of accessible bite angles. So next, I will talk about the another class of ligand, which is isonitriles. So isonitriles is a two electron ligands. It is a L-type ligands. It is a L-type ligand which closely resemble to the CO. So replacement of the CO oxygen atom of CO with the related the N atom, the less electronegativity fragment Rn give the isonitrile or NCl a ligand that is significantly is a better electron donor than the CO. So sigma donation property of the isonitrile is better compared to the carbonyl because the more electronegative oxygen atom is replaced by the nitrogen. So the isonitrile stabilize more cationic and higher oxidation state of the metal center compared to the CO. Is stabilize higher oxidation state of the CO in metal center compared to the CO. CO is preferably bound to the low valent metal center. So that is one example where this PTC and PH whole 4 whole 2 plus is known, but POCO whole 4 2 plus is not known because here the oxidation of platinum is +2. So carbonyl ligand is not that much sigma donor, so it will not stabilize the +2 oxidation of platinum, but the isonitrile can stabilize the +2 oxidation state. So that's why this complex is known for isonitrile but not for the CO. So the lone pair of CO so main difference is the electron donation is that the lone pair of the CO is almost non-bonding, while in the isonitrile it is more anti-bonding. So when sigma donation take place from the anti-bonding orbital, so it will stronger the CN bond, but pi back donation weaken the bond. So the shift in the IR will depend on the strength of sigma and pi donation. And the isonitrile is more sensitive to nucleophilic attack at carbon to keep the amino carbons, and it is a higher tendency for migratory insertion reaction. And unlike the situation of the carbonyl, the isonitrile stretching vibration in the complex is often lower than in the free ligand. So deflection of the electron density in this lone pair by donation to the metal center, that has little effect on stretching frequency of carbonyl, but it is a very much effect on the isonitrile. Back donation also lower the stretching frequency of the both CO and isonitrile, depending on the balance of the sigma donation versus pi back bonding. So higher stretching frequency is raised for weak sigma donor pi donor ligands and lower for strong pi donor ligands. So that means when and isonitrile can bind in two mode when the when the back bonding is not strong, it will bind as a linear fashion. This is the, and when the back donation is the more strong, it will donate, it will bind like a bend fashion. So bend means the structure of the bend fashion is in this manner, in this bend fashion. When the more back donation, it will favor the this conformer. So one example is NBClCO Sienna TMP. The ligand is bent at nitrogen angle is 129 on 150 between the 150 144. So our next topic is a nitrosyls. So nitrosyls is a NO. It is a stable free radical. So because the NO bond is the dimer is very weak. In surprising development, also found in important biological signaling having a biosynthetic pathway, a specialized sensor protein. As an alternative to using free NO for synthesis, the nitrosyl compound NO plus available as a salt like NOPF4, and NO plus is isoelectronic with the carbonyl. So it can replace the CO in the substitution reaction. In the majority of the nitrosyl complexes, M-NO unit is a linear. In such case, NO is usually considered as a 2-electron donor on an ionic model, but 3-electron ligand on covalent model. So NO plus, it can is a 3-electron donor in the covalent model, and when NO is bind as a bend fashion, it will is 1-electron donor. It will like the X type ligand. So NO binds in 2A, either NO plus that will give a linear molecule that will be a 3-electron donor in the covalent model, or NO minus that will give the bend molecule will be an 1-electron donor. So this is the electronic structure of NO and is binding the metal same fragment on the covalent and the ionic model. In the covalent model, when it binds in the linear fashion, the NO, the non-bonding electron is donated to the vacant d orbital of the metal center, and there is a back bonding between the metal, partial back bonding between the metal d orbital to the this unpaired electron of NO. And but when it bind to the metal center, it via the bend fashion, the rehybridize to the n orbital to the sp2, and it will pointed to the metal center, and there is a bond between this M and N orbital. And another, when is bind to the ionic model, so when it is in the linear fashion, electron transfer from NO to MLN bond, and this is in NO plus. Then NO plus will donate the electron to the vacant d orbital of the metal, and it extract the electron from the field d orbital to the metal center. And when it bind to the bend fashion, the electron transfer from the metal to NO happened, and this is NO minus, and then the electron donation from the metal nitrogen orbital to the metal is happening. So this is the all about the nitrosyl ligand. So it will be depending on the electron density of the metal center, the binding mode of the NO can convert it to the linear or bend. So linear conversion of linear to a bend NO is considered to the lead the increase in the formal oxidation state of the two units. So raising the electron density of the metal will encourage the linear to bend conversion, because in the bend NO is a pair of electron originally assigned to the complex become a lone pair of nitrogen. In the ionic model, the electron is metal reduced the NO plus to NO minus. So the electron density on the metal center will affects the coordination of nitrosyls. So if the metal is more electron rich, it will favors to reduce the NO plus to NO minus to bind is a bend fashion. So now I will discuss some questions. So first question is, consider the following this reaction. So in which case the ligand substitution reaction occur faster when this L is equal to CO and L equal to PMe3. So here nickel, the oxidation state of the nickel is 0. So it is nickel is 0. Nickel is 0 oxidation state, and the total electron count of the nickel is 10 plus 8, 18 electron case, 8 electron, both 18 electron. So for both when L is equal to CO or L equal to PMe3, so both case the nickel is a 18 electron complex. So in both case it is a totally saturated molecules. So that this ligand substitution will follow a dissociative pathway, but here the dissociation of the one CO molecule rate will depend upon the bond strength of the nickel CO bond. So when the stronger the nickel C bond, there will be a slow rate. So first we have to consider the electron donation property of the CO and PMe3. So when PMe3 is a strong donor, sigma donor, but it is a poor pi acceptor ligand. But CO is a strong sigma donor, but it is a good pi acceptor ligand. So when here PMe3 is present, that case the electron density of the metal center will increase. So that will favor the more back donation from nickel to this carbonyl. So that means when PMe3 there is a more back donation between the nickel and carbonyl, so that will stronger the nickel CO bond. So the reaction will be, the rate of the reaction will be higher for when L equal to CO, and reaction rate will be slower when L equal to PMe3. So next question is the, among these two complex, chromium CO whole 5 PF3 or chromium CO whole 5 PMe3. So which have the stronger CO bond and which has the stronger chromium carbon bond. So here The structure of the compound is chromium, CO, 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 and P, R, P, R3. When R equal, one case is PM3 and one case is PM3, PME3. So the metal, the chromium, the bond strength of the chromium carbon and the bond length of the this carbonyl will depend on the electron donation property of this PR3 group. So more will be the electron donation to the metal center that will favor more back donation to the metal to carbonyl, and that will strengthen the chromium carbon bond, and shorter that will increase the CO bond length. So here between this PF3 and PME3, between this PF3 PME3, PME3 has more electron donation to the metal center compared to the PF3. So in the case of PME3, the more electron density on the metal center, and PF3 is disfavor the back donation to the metal to carbonyl. So for the first question, which has the stronger CO bond? So stronger CO bond means when there is a less back bonding to the metal to carbonyl, that will strong. There will be the stronger CO bond. So in this case, for question number A, so PF3 is it has reduced the electron density from the metal center more compared to the PME3. The PF3 is a more backbone except the electron from the metal center, so it will disfavor the back bonding between the metal to carbonyl. So for PF3 case, the CO bond length is stronger CO bond compared to the PME3. And for question B, which has the stronger carbonyl, chromium and the carbon bonds. So between this PF3 and PME3, PME3 has more sigma donation property compared to the PF3. So PME3 will increase more electron density on the metal center. So that will favor more back donation between the Cr, chromium and the carbonyl. So that will strengthen the metal carbon bond. So for PME3 case, the stronger the chromium C bond. So next question is the arrange the following the decreasing order of rhodium metal, this rhodium carbon bond length. So this metal carbon bond length will depend upon the electron density on the metal center, and this electron density will more or less depend on the electron donating property of this phosphine ligand. So more will be the phosphine, which phosphine ligand has more electron donating power, that will increase the electron density to the metal center, and that will favor more back bonding between this metal to carbonyl, and that will decrease the metal carbon bond. So here total PPH3, PET3, and P6H C6F5C whole 3. So between these PET3 has more electron sigma donation property compared to the PPH3 compared to the P6HF5 all 3. So more electron donation from when the PET3 is present, so that will favor in the PET3 case. There will be more donation between the metal to carbonyl, that will shorten the metal carbon bond. So the order is the metal carbonyl bond is B A C. So complex B has more shorter metal carbon bond compared to the other. So our next question is, if the highly substituted complex MCO whole 3L3 is a desired, which of the ligand PME3 or P tart butyl whole 3 with preferred, and why? Name of the isomer formed from that reaction. So highly substitution reaction means so here the formation of this complex is strongly depend on the steric bulk of this phosphine ligand. So which phosphine ligand has more steric bulk, that will disfavor the formation of this complex. So between the PME3 and P tarbutyl C3, so this one has more cone angle, that means it has more steric bulk around the, it will create more steric bulk around the metal center. So cone angle P tart butyl whole 3 is more sterically hindered compared to this PME3. So that will create more steric bulk around the metal center, and that will disfavor the formation of this MOCO whole 3 L3. So for the PME3 case, it is preferred due to the less steric bulk around the metal center, and it will form this MO CO P Me3 PME3 and PME3, and the isomer is the facial phase isomer. So my next question is, the place the following dinitrogen complex in order their increase NN bond length. So here the NN bond length depend upon the back donation from metal to this nitrogen. So there, if there is a more back donation to the metal to nitrogen, there will be there will be increase in the NN bond length. So between these four ligand, so electron donation property, sigma donation property of PF3 PF3 is less compared to the P OME whole 3 compared to the PPH3 compared to the PME3. So PME3 has more sigma donation property among these 4 ligand. So for this P, when this PME3 is present, so that case there is a more electron density on the metal center, and it will favor the more back donation to metal to nitrogen faster orbital. So that case the NN bond length will be higher compared to the other, and PH3 is a less sigma donating ligand. So that case the metal ligand metal to the metal to the nitrogen back donation will be less favorable, because the pH will be more electronegative. It will decrease the electron density from the metal center. So in that case the nitrogen bond is more shorter. So the order is, if this is 1 2 3 4, so for 3 has lower NN bond length compared to the 4 compared to the 1, then compared to the 2. So our next question is, consider the following data and explain the observed trend in the reaction rate. So here molybdenum CO whole 4 L2 plus CO, molybdenum CO whole 5 L plus L. So in this case one L ligand is substituted for by the carbonyl. So here one dissociation on one L ligand is happened. So reaction rate is high for PPH3 ligand. This is the rate of the reaction for all these 3 cases. So here the dissociation of the L will depend upon the steric bulk of this PPH3 ligand. So if there is a large cone angle of this phosphine ligand, so in that case the ligand dissociation will be more facile. So between these 3, the cone angle is high for PPH3 compared to the PPH2ME compared to the PPHME2. So PPH3 here is a more steric bulk compared to the other 2. So it is increase of the steric bulk. So in that case the ligand dissociation will be more favorable. So that's why the rate is more for this and rate is more less for this PPME2. So our next question is, among the given phosphates are most like to give positive reaction in the given scheme. So here on PPH3, 2 PPH3 ligand is substituted by this PR3 ligand. So here the variation of the PR3 is a 4-fluoro C6H4, and another case is P-tarbutyl whole 3, another case is PET3, and another case 4-methoxy. So here the ligand substitutions will be favored for which phosphine ligand has the more electron donating property compared to it has more electron donating property than the PPH3 ligand. So between these four ligand, for this ligand 1 there is a proto substituted, so this will less sigma donating compared to the PPH3, but the all other case there is the electron donating substitution on the phosphine atom. So that for these three cases the more sigma donating property of the phosphine, so our reaction will be more positive for this B, C, D, but it will due to the more basic nature of this all three ligand compared to this PPH3, but electron the reaction will be less favorable for this ligand. So our next question is, NO plus is an isoelectronic with CO and often replace the CO in the substitution reaction. So it might seem that if this reaction is favorable reaction or not. So here the MOCO whole 6, here the molybdenum oxidation state is 0, and here the oxidation state of molybdenum is plus 6. So we know that NO plus is isolated to CO. It often replaces the carbonyl in the metal complex. So, but in this case, there is a change in the oxidation of molybdenum to 0 to plus 6. So that's why this reaction is not favorable, because the changing of the oxidation NO is not that much electron donating that will favor the plus 6 oxidation state of the molybdenum. So this reaction will not favorable, because this is changing of the metal oxidation by plus 6. Normally there is a changing in the plus minus 2 oxidation, changing in the oxidation state in the 2 digit will be favorable. So this reaction is not favorable due to the higher change in the oxidation of the molybdenum. So thank you.